slides.
No, these
All
are
right.
5.
Okay.
Come on, tell us the one.
All right. Well, it's Wednesday, and we are continuing on. If it's not in a good order, I blame the textbook because I'm kind of following along with parts of the textbook now. I take responsibility for my own content here. Okay. Well, on Monday we did maximum likelihood estimation, and what did we say? We said, to maximize the likelihood of our data, we want to figure out the parameters that go into W, which are, linear regression. It's our slope and intercept terms, or basically just that vector of weights in your thing. And then we said, well, we're going to model our data as things come, being centered around W transpose Xn, centered around what our model would predict. And then we said the actual values that we observe are normally distributed around this W transpose X, right? And then, so if you do that, then you have the PDF of the normal distribution, and we said, what's the probability of getting each observation? We got n of these. We take the product of all of them because they're all independent of each other. What do you do if they're not independent? It's like things blow up, right? You have a huge product instead. Of what, conditional terms? Okay, well, anyway, so we take the product of all of these things. We said, okay, well, you know what? And then when we do the log likelihood, we said, hey, you know what? This boils down, after we apply the log, this boils down to the sum squared errors. Should I close this door? I'll close the door. I have it open because you can't. They're working to keep the place clean, but then it's like only the back, the rear entrance is unlocked. Okay, well, anyway, when we take the log, we notice there's this very similar structure. This quantity over here, the target value minus W transpose Xn, this is your residual. You're squaring it and you're taking the sum of it, right? So this is your sum of squared errors. And it's multiplied by a negative constant. And so we said we want to maximize the likelihood. Maximizing the likelihood, finding the values that maximize the likelihood are the same values that maximize the log likelihood. And when we look at this structure, we see all of these are constants with respect to W. And so therefore maximizing the log likelihood is the same thing as minimizing the sum of squared errors. And we could have skipped Monday's lecture and just said that too. But we worked it out, which was, I guess, fun. I don't know. And then, so we got this, right? The value of W that maximizes the log likelihood is this thing, which is the exact same thing that minimizes the sum of squared errors. And that works out if you assume your errors come from the normal distribution. One thing was that this solution for the W that maximizes the likelihood doesn't include the variance term, right? So we say, okay, well, what if we wanted to maximize the log likelihood with respect to the variance? Okay, well, we do the same thing. So here's our log likelihood, and now we take the derivative with respect to sigma. We're going to set that equal to 0 and solve for sigma. And so so this is what we get. And okay, so this is a constant, so that zeroes out. We got negative n log sigma. So the derivative of that is negative n over sigma. And then we got negative 1/2, sigma to the negative 2. And so when you take the derivative of that, you got a negative 2 that multiplies with the negative 1/2 and eliminates it. And it becomes sigma to the negative 3. And then, with respect to sigma, this whole thing over here, it looks like a complicated thing, but it's this entire summation thing, it's just a constant with respect to sigma, right? So we're going to just leave it intact, just like that. Okay, now I set that derivative equal to 0, and we're going to solve for sigma. So, assuming sigma is not 0, we which would blow up the whole thing, right? If you have 0 variance. So obviously sigma can't be 0. Okay, so we get n over sigma is equal to 1 over sigma cubed. I multiply both sides by sigma cubed and divide both sides by n. So now I get sigma squared is equal to 1 over n times this. Okay, and what is this? Okay, well, this is basically the mean squared error. So the maximum likelihood estimate of your variance turns out to be the mean squared error of our model. And yeah.
Is there any benefit of taking like the derivative with respect to sigma versus like the derivative with respect to sigma squared?
Oh, I mean, you could take it with respect to sigma squared, and I don't know, what do you change of basis type of thing? You gotta, or just
more that like if you do n log sigma, like if you plot a factor that have like n over 2 log sigma squared, then you are only working like with one variable, so that you don't have to.
Yeah. I mean, I guess, yeah. You could do that too. I think you'd arrive at the same result. So, but yeah, okay. So this we just get the solution is the mean squared error of our model, and I guess that's interesting. Yeah, if you had to kind of estimate your variance. If you assume this is your mean, right? What's the variance? It's kind of your you take the squared distance from the mean, okay, and then you add them up, and then our unbiased variance is you divide by n minus 1. But actually, the one that's going to maximize your likelihood is you divide by n. Okay. So anyway, that's going to be the value of sigma that maximizes your likelihood. If we plug this back in to our log likelihood, okay, so I'm going to plug back in basically if I say, okay, anytime I recognize this, I'm going to plug in sigma squared hat, okay, so I've got that right here, okay? So we can say we're going to replace this, okay, with n times sigma hat, right? So this, if I multiply both sides by n, I got n sigma squared is equal to this sum of squared errors. So I'm going to replace the sum of squared errors with n sigma squared hat. And then we're going to kind of plug in the sigma squared, sigma hat squared or sigma squared hat, I don't know, whatever, into our estimates all over the place, okay? And then so these kind of cancel out, and then and we get this, and we can kind of combine these things, and we get, this is our estimate of the log likelihood of at the maximum. All right, and so if you look at this, we have, this sigma squared, okay, the sigma squared hat, all right? We've got the log of it, and then we've got a negative, right? So we have a negative constant for this, and so the log likelihood is going to keep going up, right? Because if we keep shrinking this thing. So if we keep shrinking sigma squared hat, the overall log likelihood is going to keep going up. And so if you think of sigma squared as the variance of the error in the model, okay? The error is kind of your leftover variation after we make a prediction. It's just how much is left over between the actual value and our prediction, W transpose X. And so one way to kind of decrease is to keep kind of tweaking that prediction, that W transpose X, right, W transpose Xn, to keep making that as complicated as possible so that you get less and less and less of a difference between T sub n and W transpose X sub n, right? So if we keep shrinking this, then our log likelihood is going to keep going up. And so, again, we run into this kind of bias variance type of situation where we say, all right, you know what, we can keep increasing the complexity of the model, and that's going to maximize the likelihood, okay, of our data in terms of we're shrinking our errors to be as small as possible. But again, we also know making a super complicated model is not a great idea, right? But that's not reflected. Again, if you have a single-minded goal, right, minimize the sum of squared errors, which turns out to be the same thing as maximizing the likelihood of your data, right? If you have this kind of single-focused thing, you end up making non-optimal choices, and that's not just for this, but it's like all of life too, right? If you can only focus on one thing and you say that's the most important thing, and everything else, it doesn't matter, we're gonna ruin friendships and stuff just so I can eke out 1% more of something, that's what you'll get, okay? But holistically we go, okay, you know what, maybe just maximizing the likelihood of our data is not the best approach, okay? This brings us to our next favorite topic, Fisher information, where we can talk about how much information do we have, how much information is available in our data, right? And so we got a bunch of kind of definitions of what Fisher information is and what information is, but we'll take we'll look at kind of one aspect of it in today's lecture. Let me go ahead and give you your first view quiz answer, which is the letter A. A as in apple. A as in apple. Okay, so we're going to rewind a bit, and we'll just talk about derivatives and second derivatives and things like that. All right, so the first derivative tells us the rate of change, all right? Slope of our tangent line, if we're thinking of just a single function. And then the second derivative tells you how quickly the slope changes, right? And it reflects the curvature of the function. So if you have a large absolute value of your second derivative, that means the slope changes rapidly. So that indicates a sharp turn, okay, a sharp bend in the curve, right? So your slope changes rapidly, so the curvature is changing. You got high curvature, the slope is changing rapidly, right? And then the sign of the second derivative, whether it's positive or negative or zero or something, is, it tells us about the concavity, right? You got concave up and concave down. So you got a positive second derivative, means the concavity is up, meaning you go from kind of negative slope to positive slope. So you got this kind of this U thing, whereas a negative one, you go from positive slope to negative slope. So you've got kind of this, this hill type of thing. And then your zero second derivative would be you either don't know the concavity or it's an inflection point or something like that. Okay, but the kind of the magnitude of your second derivative tells you how rapidly is the slope changing. Okay, we have kind of the multivariate equivalent of the derivative, which would be our gradient. Okay, and so for the gradient you have some kind of multi-dimensional function that takes in multiple real numbers, but the output is just one value. Okay, so it's not we don't have a high dimensional output, just a single value. So this would be things like our loss function, right? You've got multiple parameters coming in. You've got some vector of W values, and you have your data coming in, and the loss is just one single number. Okay, and so our input vector is some vector of weights or something, and so the gradient of this function, usually our loss function with respect to W, is going to be a vector, and it's a vector of all the partial derivatives, right? And so we can think of this, the gradient as kind of the multivariate generalization of the derivative. And so if we want to kind of think of what's the second derivative, then we would take, all right, what is the kind of second derivative of this thing? Now we're going to get a matrix of all the second kind of partial derivatives of f, right? So if all of the second partial derivatives of f are continuous over the domain, then we get what we call the Hessian matrix, all right? And so the Hessian matrix is going to be an n by n matrix. So you got, n terms in W, which is admittedly confusing because we also use n for how many observations we have. But here we're saying n here represents how many values we have in W. I guess we could have used another letter, K or something. But you get this square matrix, right? And so you get the partial derivative of f with respect to W1 and W1, W1 squared. And then you get the partial derivative with respect to W1 and W2. And then over here you have partial derivative, okay? So this is a matrix of second derivatives, and we can think of this as kind of our multivariate generalization of the second derivative, but now we get this square matrix, the Hessian, right? Did you guys cover this in like 32A? Okay, yeah. It's good times, right? Okay. All right. You can one way to think of this is you can say, all right, what we're going to do is we're going to take, so our gradient is this this vector of partial derivatives, and you can think of the Hessian as also, okay, each column is going to be the gradient of each term in your gradient, right? So you're going to think of, you take the quote-unquote gradient of the partial derivative of f with respect to W1, and you're going to get basically this column of terms here. Partial, this, second derivative with respect to W1, and second derivative with respect to W2, and so on and so forth, or the derivative with respect to W2, so on. And that's how we build this whole thing out, okay? So, when we have a univariate function, and we look at the sign of the second derivative, that tells us about the concavity of the function. And when we have a multivariate function, there's this concept of the definiteness of a matrix. So, it's kind of, I guess it's like the version of having a sign, okay? And so if the gradient of a function is equal to 0 at some point, and the Hessian matrix, you think of the sign of it as either you have positive definite, negative definite, or neither. So positive definite means all the eigenvalues of the matrix are greater than 0. Then your function is concave up, and your location x is going to be a local minimum, okay? If you've got some point x where the gradient is 0. If you have a negative definite matrix, all the eigenvalues are less than 0, then you have this concave down thing. So again, you can kind of think of this as like, I think it's easy to go from one dimension to just imagining 2 dimensions, right? So rather than having, a line that, kind of makes this hill, now you have a surface that makes a hill. And there's kind of and it's hard for us to imagine anything higher than 2 dimensions. But there's like the higher dimensional equivalent of that we can't really picture in our brains. But you have this kind of this concave down shape, right? And then if you have kind of this mix of both positive and negative eigenvalues, then it might be a saddle point, okay? And if you have eigenvalues that are equal to 0, then that makes it hard. Okay, but you can kind of think of, now you have this multi-dimensional kind of aspect to it. Okay, other ways to think of the Hessian matrix is the Hessian matrix is the equivalent to the Jacobian matrix of the gradient function, which is basically what we have here, right? So you have this vector, and if you take the derivatives of that, you can think of that as the Jacobian matrix of the gradient function. The Hessian matrix is usually symmetric, okay? It might not be symmetric if you have second derivatives that are not continuous. And so I think back here we said so part of this thing about the Hessian, we said if all of the second partial derivatives are continuous, then it works out nicely. But yeah, if you have something, if you got like an absolute value as part of your function or something, then things break. so we like having nice smooth functions to kind of keep our second derivatives continuous. But yeah, sometimes it breaks. Okay, and then if the second derivatives are continuous, then the order of differentiation does not matter, and that's why it ends up being symmetric. So like here we get, here we have the partial with respect to W1 and W2, and here we have the partial with respect to W2 and W1. Or am I reading that backwards? But basically how we, if they're continuous, then these two things are going to be the same. Okay, so we're going to get a symmetric matrix. Okay. So yeah, the Hessian is useful for us because it tells us about the curvature of the function. And so when we apply it to, say, the likelihood or the log likelihood function, we get an idea of the curvature of the function, and that in turn tells us how confident we can be in our parameter estimates. So I'm going to do kind of a univariate example at first. My hope is that it shows how the second derivative tells us how confident we can be in our parameter estimates. Okay, so we're just going to look at a single univariate probability function, and then we can try to generalize it to a multivariate case. Right? So again, imagine we're dealing with this. We've got some kind of bag, and inside this bag, I got a donut. But inside the bag, we're going to pretend we got red marbles and blue marbles. Okay, and we want to figure out what proportion is red. Okay, so we've got some value theta, and we don't know what proportion is red in the bag, but we're going to draw marbles with replacement to try to get a guess, right? So it's kind of like whenever you do some kind of political survey, there's some proportion in the population that has a certain opinion, right? And then you draw people at random, and based on what you see in your sample of people, you try to get an estimate of what exists in the population, okay? But we're going to just simplify it. We got I picked red and blue marbles, not intending to be political here, but here, okay, so anyway, we have, we're going to say we draw 10 marbles with replacement. We get red marbles 4 times, okay? And so our data is we get 4 red marbles out of 10 draws, and therefore the likelihood of our data, if we're assuming a Bernoulli thing, and for this one particular sequence, okay, is going to be theta to the 4 times 1 minus theta to the 6. If we wanted to make a binomial, we could add in, 10 choose 4 or whatever. But this is what we have, okay? And so I can say, all right, what does the likelihood function look like? And I can plot all the values from 0 to 1. And we're going to just plot theta to the 4 times 1 minus theta to the 6. And I plot this, and this is what our function looks like. And we see the likelihood function has a maximum at theta equal to 0.4, which aligns with our intuitive sense. But also because we don't, we only had 10 observations. If someone says, could your theta be 0.5? We'd say, yeah, that seems pretty reasonable. Could theta be 0.6? And it's also like, it's not that strange to imagine that the bag actually is 60% red, and just kind of by random luck, we got 4 out of 10, 4 red out of 10. Okay, the bag could also be only like 20% red. Okay, and just by kind of random luck, we got 4 4 red out of 10 marbles, right? Whereas, getting, like, if the bag was only 1% red, that would be really shocking that we managed to get the red marble 4 times, okay? And if the bag was something like 80% red, that would also be really shocking that we only got red 4 times or something like that. So this is kind of our likelihood function, and this shows us, our likelihood is maximized when theta is equal to 0.4, which makes intuitive sense. Okay, so that's what this says. What if instead of drawing a marble 10 times, I drew a marble 1,000 times, drew 1,000 marbles with replacement, and now I got 400 red marbles out of 1,000 draws, okay? Now how confident are we that the proportion is 0.4 in the bag? Okay, we're a lot more confident because I've got a lot more data to back this up, right? And our plot will reflect that. So if I do theta to the 400 times 1 minus theta to the 600, this is what the likelihood plot looks like, okay? So it's very narrow and pointy, okay, at theta equal to 0.4. And really, the only values that we would say are acceptable or reasonable are values that are very close to 0.4. So if someone said, okay, the bag isn't actually 40% red, it's 41% red, we would accept that, okay? But if somebody says, I think the bag is 50% red, we would say, no way, okay? Because, if it's 50% red, how do you explain the fact that I only got 400 red, right? Only 400 red out of 1,000 marbles. That seems really strange, okay? Or if the bag was 30% red, there's no way I would have gotten 400 red out of 1,000, right? Versus over here, if it was 50% red, easily I could get 4 out of 10 red. But if it's 50% red here, there's no way, right? The likelihood of it being 50% red is practically 0 because what I got was 400 red. So really, to get 400 out of 1,000 draws, 400 red out of 1,000 draws, really the only really acceptable values are things like 41% red, 39% red, maybe 38% or 42% red. But once you start straying from 40%, the likelihood becomes really unlikely, right? And so if you look at what is the second derivative, what is the second derivative? How rapidly is the slope changing at these locations, right? So what is the magnitude of your second derivative? Here, we've got something that's concave down. At this point, 0.4, it's concave down. We're going from a positive slope to a negative slope, but the change is kind of this nice, gentle change in slope, right? It's like, imagine the roller coaster ride. This would be like a nice little hill to go over. You're not gonna be shocked, okay? All right. Over here, the change in slope is really rapid, and I think this would be actually impossible for a roller coaster. You would sustain way too many negative G forces, and something bad would happen. But your track would break. But basically, the change, we're going from very steep positive slope to very steep negative slope, right? So we have this very rapid change in slope. We have a very high, large second derivative there. Okay. So I just said this pointiness, right? So the graph is much more pointy. Okay. I don't know what the what's a better term for this, okay? But kind of this tells us, the fact that it's very pointy tells us that only values that are close to 0.4, like 0.39 or 0.41, have high likelihoods. And we have kind of much less variance in what theta could be, also indicating that we have kind of much more confidence in our estimate based on the amount of data we have. Okay. And so how much curvature reflects kind of the amount of information that we have, okay? How much information we have about our parameter estimate is kind of reflected in this concept of the curvature of the function here, the curvature of our likelihood function. So here, actually, so before we get into this slide, let me give you your second view quiz answer, which is the letter E. E as an elephant. E as an elephant. Okay, so here, I take the second derivative of our likelihood function when we have 10 draws. I take the second derivative of our likelihood function when we have 1,000 draws, or I guess the log likelihood. And so if I do this, I get, over here I have 4 log theta plus 6 log 1 minus theta. My derivative is 4 over theta plus 6 over 1 minus theta. And here I have the second derivative, negative 4 over theta squared plus negative 6 over 1 minus theta squared. Okay, same thing with the 1,000 draws, second derivative. Basically, I end up with the same thing, but times 100, right? Negative 400 over theta squared plus negative 600 over 1 minus theta squared. Okay, so this thing is 100 times larger than this one, and that actually kind of makes sense because here I've got 100 times more data. I've got 1,000 draws versus 10 draws. And if we were to plug in our value of 0.4, okay, our estimated theta value of 0.4 into each of these things, here I get kind of this, the value I get here is negative 41.667, and over here I get 100 times that, negative 4,166.7, okay? And so this, the second derivative, which measures the curvature, says we have 100 times more curvature here, so it's much more kind of pointy, much sharper second derivative, or the function makes a stronger point, and it reflects the amount of information we have about our estimate. And that's one way to look at the Fisher information. Okay, so the fact that the likelihood function has much more curvature in the second derivative means that the data we have provides more information about the location of theta. And again, it makes intuitive sense just because one was based off of 1,000 draws versus the other was based off of 10 draws. So we have, literally 100 times more information about the location of what theta should be. And so the relationship between the curvature of the likelihood function and the information that we have about the parameter is, I guess, one aspect or one way to think about Fisher information. So the Fisher information, okay, one possible definition is this, okay? So we're going to say, the Fisher information is a way for us to kind of measure how much information a random variable can provide about the unknown parameter. Formally, the definition of the Fisher information is that it's the variance of the score, and the score itself is the derivative or the gradient of the log likelihood. Okay. So if we have some kind of probability density function or even a probability mass function, okay, if we say if the log likelihood is twice differentiable with respect to your parameters theta, okay, then the Fisher information is also going to be equal to the negative of the expected value of the second derivative of the log likelihood. So that's like a mouthful, right? But this is what we can say. So this I of theta is the Fisher information of theta. We can say is the negative of the expected value. So basically I've got the second derivative of the log likelihood function, okay, second derivative of the log likelihood function, and we're going to take the negative expected value. Okay, we can also just write negative expected value, and the expected value is taken with respect to the random variable x, okay, and the distribution of x is defined by f of x theta, okay? So we're going to say, because we're saying, do we take the expected value with respect to what, okay, to theta or what? No, we're taking the expected value with respect to x here. Okay, so negative the expected value of x has this PDF or PMF of f of x here, okay? And we're taking the second derivative with respect to theta of the log likelihood. Okay, so if we have a Bernoulli, this looks way more complicated than it is. It's exactly what you would expect it to be. But let's say we have a Bernoulli function, right? Or a Bernoulli random variable. So this is the PDF or PMF of a Bernoulli, okay? It's theta to the x, 1 minus theta to the 1 minus x. X can be 0 or 1. And we're going to take the log of this, and we want the second derivative of this log likelihood function. So we're going to have log of theta to the x, log of 1 minus theta to the 1 minus x, and we're going to take the second derivative with respect to theta. So so here I get x log theta, 1 minus x log 1 minus theta, and then I have the derivative with respect to, the first derivative is x over theta and this, and the second derivative is going to be this, okay? Negative x over theta squared and negative 1 minus theta, negative 1 minus x over 1 minus theta squared. Okay, and then so our Fisher information is the negative expectation of this random variable, right? What is the negative expected value of x? Okay, so we're going to get e of x and e of 1 minus x. And for Bernoulli random variable, the expected value of x is just theta. Okay, so we're going to get theta over theta squared and 1 minus theta over 1 minus theta squared. Okay, so if you say, what is the expected value of your random variable x? So this is what we get. And then so you're going to get 1 over theta plus 1 over 1 minus theta. And you can kind of multiply both sides, or multiply the top and bottom by 1 minus theta or whatever. You combine these fractions. And it simplifies to 1 over theta times 1 minus theta. And so that's the amount of information that we get for for theta based on one observation of the Bernoulli. Okay, the Fisher information is additive, and so here, I just wrote the Fisher information is additive. So with n observations, we're going to get this. But you can also work out the math yourself if you wanted to, right? You could say, all right, what if I have n observations, n observations from Bernoulli distribution? Okay, you're going to have some basically a product of n of these things. Okay, and then you're going to have basically the sum of your x's instead. And you're going to get, if you do all of this, you're going to get the sum of your x's and then n minus the sum of your x's, and then if you solve it out, you're going to get this result. Okay, but you can also just kind of take this shortcut and just say the Fisher information is additive, and so if you have n observations, you're going to end up with n over theta times 1 minus theta. Okay, and that aligns exactly with what we had, right? So we had a certain amount of information with 10 observations, and we had 100 times that when we had 100 times as many observations. So when we had 1,000 observations, it was 100 times that, or basically for one observation we had 1 over theta times 1 minus theta. Where did it go? Okay, so with 10 draws we had this, and then if we 10 for one we would get something 10 times that, 1,000 times that. It all just kind of grows in relation to our n here. Okay, so same kind of idea. So this Fisher information concept applies to the multivariate case. Okay, so we're going to generalize this to the multivariate setting, and so the second derivative in the multivariate setting would be our Hessian matrix. And so the Fisher information matrix now for a multivariate function tells us kind of how much information our data provides about our unknown parameters theta, okay? And so here, the Fisher information is going to be the negative expected value of the matrix of second derivatives of the log likelihood. So here's our Hessian matrix. Okay, so we have the Hessian matrix of the log likelihood function, and it's going to be the negative expected value is going to be kind of our Fisher information matrix. All right, so let me go ahead and give you your last view quiz answer for today, which is the letter A. Letter A as an apple, is your last view quiz answer for today. So, so if we if we do this for linear regression, the unknown parameters here are thetas, that are the unknown parameters are actually going to be the coefficients W, right? Our slope and intercept, or however many terms that we have in W. Again, we're assuming our errors are normally distributed. Probability function of each observation is going to be the PDF, or we're going to say the mean is this, our prediction, and we got our sigma squared values. We're going to treat the observed values, right? Our x sub n's and our sigma, our variance, we're going to treat that as fixed. The only thing that really can change here is our w's, okay? So the Fisher information is the negative expected value of the Hessian of the log likelihood. The expected value here, okay, and this is the part that feels a little bit confusing, or it could be, is that it's taken with respect to the outcome variable. And in this case, our outcome variable is t, okay? The actual values that we've observed, right? And the t values are defined by the probability function, which is, our normal distribution, centered at W transpose X with variance sigma squared, okay? So, for the normal distribution, our expected values are, for T sub n will be this W transpose X sub n. Okay, so we have this big Hessian matrix of second derivatives, partial second derivatives with respect to, the PDF of this thing, okay? And so, if we expand this out, this is our log likelihood. And we're going to say, okay, what is the first derivative of the log likelihood? And we get this. And so we've worked this out before. And then what is the second derivative of this thing? Okay, so the second derivative with respect to W is going to end up being negative sigma squared X transpose X, right? And so this is going to be our big, kind of our Hessian matrix. And sorry, I know my letters have changed, so that, our W now has K terms in it rather than N terms in it. But so now we have this, this square matrix of this K by K square matrix, and it's equivalent to basically, how many columns did you have in X, okay? And so X transpose X, negative 1 over sigma squared there. Okay, and so, with respect to this outcome variable, okay, there's actually no t sub n's here. Okay, so we just say, all right, well, all these things are just constants. So the negative expected value of this thing just ends up being 1 over sigma squared X transpose X. Okay, so, if there was something about t kind of being in here, maybe we'd have to figure out the expected value. But with respect to the outcome variable t sub n, these are all constants here. So so this is kind of the result where we arrive. So this is the Hessian matrix of the log likelihood, negative 1 over sigma squared X transpose X. What's the expected value, negative expected value of this thing? And this is what we have. Okay, so what is this? What does this mean? So the model of our data, is that the actual values are centered around W transpose X of n plus some epsilon, okay? Sigma squared is kind of the amount of variance that we have in this noise parameter epsilon. So how much, if the actual value is this line, how much scatter do we have around that? And so we can kind of see that, part of the Fisher information that we get is directly related to our sigma squared. So if there's a lot of noise, if sigma squared is a big value, our Fisher information is going to be smaller because this is in our denominator, right? On the other hand, if there's very little scatter, we're going to also have a lot of information, right, about our parameters. One thing we left off is this other part, X transpose X. And this reflects how much information do we get from our x variable? And so I think I have this in kind of Friday's lecture, but you can think about if you have just if you needed to estimate a slope. Okay, so all right, you're trying to estimate, the slope for, I don't know, how much a plant grows or something, okay? And so you measure like, okay, how much did, what is the height on this day? What is the height on the next day? What is the height on this next day? What's the height on this next day, right? So is your estimate of slope going to be better or worse if you're taking measurements over, say, several years versus just a couple days? And so, your estimate's going to be much better if you have a large range of x, right? So if you can say, okay, this is how tall it was, at 1 month old, and this is how tall it was at 5 years old or something, assuming that this plant continues growing linearly over all 5 years, you're going to get a pretty good slope, right? But if you're going to say, all right, this is how old it was at 1 month, and this is how old it was at 1 month and 3 days, and you're trying to estimate, okay, based on how much we saw it grow in the last 3 days, now I want to project how much it's going to grow over 5 years. Even if it's like totally linear, you don't have much information about that, right? So that's reflected in this x transpose x. There's an aspect, and it's a little bit hard to see, but by kind of how much range we have in our x variable, we'll get a sense of kind of how much information we can get out of the slope, right? So if we have this, if we've collected data over a large range of x values, we're going to get a pretty good estimate of our slope, versus if our range of x values where we've collected data is very small, our estimate of slope is not going to be very good. Okay, and in fact, if you've only collected x value information at one location in x, right, like it would be impossible to estimate the slope, right? If all of your information of x is at like x equal to 8, okay, and you have no value for x equal to 9 or no value for x equal to 7 or something like that, you can't estimate the slope. Okay, and if you have one observation at x equal to 9, you're going to get a little bit more information. You can start to estimate the slope, but not very good. If you have a whole bunch of observations at x equal to 9, but also x equal to 100 or something like that, you're going to get a much better idea. Okay, and that's part of this x transpose x thing. And we'll take a look at that on Friday. But we'll go ahead and end here for today, and we will see you Friday.